Welcome to another in this series about diode lasers, in which I'm busy trying to discover what's really going on inside a diode laser and how 455 nanometer light affects materials. I keep trying to escape from this 5-watt laser because there's only one diode in it, and I think to myself, I really ought to get onto more exciting things. But there are so many curiosities and things that I'm observing with this 5-watt laser that I keep being attracted back to look at just what's going on. Because one of the things that I'm considering is one laser is telling me a lot about the performance of 455 nanometer light and the way in which a diode laser works. Now, if I put two diode lasers in and go up to 10 watts, am I going to get twice as much power? Now, that's an interesting question which I have some logical arguments as to why that might not be the case. Look, let's just have a look at this piece of paper here. Here we can see the light from one 5-watt diode. It's coherent, i.e. the wavelengths are perfectly in phase with each other, and as I've described it before, it's a tsunami of light. Regard this as one side of a tug-of-war team. 5 watts, 5 people. So here we've got another tug-of-war team, 5 watts, 5 people. Now if I put them in opposition to each other, you know what the end result is. You get balance in the middle where nothing really happens. If you make these waves completely 180 degrees out of phase with these waves will cancel these waves. Before I move on to the 10-watt diode is, how have they managed to get these two waves completely in phase? Considering you've got two light paths which have got to meet up at the lens, we've got two problems. First of all, not only are we going to get this patch of light on top of that patch of light, we've got to get those photons there perfectly in phase with those photons, even though they come from a different laser source. There's a pretty challenging exercise to be investigated when we look at the 10-watt laser to see just how well this problem has been solved. So at the moment, I don't want to confuse the exercise by having another tug-of-war team pulling in the other direction. So we're just going to stay with this single 5-watt tsunami of photons, blue photons. So I want to carry out two tests now. I've got a piece of acrylic at the bottom here, and on top of the acrylic we've painted a film of that soot, the black carbon. I'm going to use 100% power, and I've got this set so that the focus is roughly 1 millimeter below the bottom of this piece of acrylic. So the laser is passing right through the acrylic, hopefully doing nothing. And yet at the bottom here, we're well out of focus, and we should see some energy transfer taking place in the carbon. Now I want to be quite close to the edge because I want to look through the edge of the material to see the damage, the depth of damage that I'm doing. 0, 1, 2, 3, 4, 5. Now did you see the way in which it started off red and then finished off blue? So we now move the head forward, and I'll remove the piece of material, and we'll run the same thing. 0, 1, 2, 3, 4. Can you see the red glow? So let's go and have a look at those under the microscope, see if we can make any interpretation about what we find. Now before I look at these under the microscope, there are two obvious things that we can see. Considering this beam is well out of focus, and this is the same beam after we've passed it through 8 millimeters of acrylic, focal point is still at the same position for both of these. One was with the acrylic in the beam and the other was without the acrylic in the beam. We've produced quite a deep, what looks almost like a spherical shaped hole. When we look at this closely, you'll definitely see that we've managed to produce bubbles in the bottom of this crater. Now bubbles means that the acrylic has boiled, which means it's got to about 160 degrees C. But some of this has obviously got above 160 degrees C because we've lost material. So it must have evaporated. So we've had a damaging effect on this material, even with low intensity light. We've actually probably done better at damaging this material with low intensity light than we did with the high intensity light. Is acrylic really transparent? We'll go and look at the spectral absorption curve for acrylic in a minute. When we pass it through the acrylic, we've got a much smaller beam. Now that means that the centre of the beam has still retained its power, but the outer part of the beam, which we're seeing here, has been filtered by the actual acrylic above it. So the acrylic has got some absorption characteristic, but the main part of the beam, which is down the centre, the high intensity part of the beam, has made it through and managed to damage this material. The other thing that I pointed out was that there was bright red glow to this initially, and then it turned blue. Well, the bright red was the carbon absorbing the energy, and it was then heating up, transferring its heat to the acrylic below, which then boiled. If the acrylic is not able to absorb the energy, then how come it managed to evaporate away? Because it means it's got above 200 degrees C. These are the sort of questions that fascinate me. Why, after the carbon black has heated up the surface, done its job of transmitting energy to the acrylic below, why didn't the damage just stop after the carbon black had burnt away? Carbon is a solid. It doesn't turn to liquid at any stage. It goes up to about 3,500 degrees C, which is very, very white hot. And then it turns into gas. There is no liquid state for carbon. So how did that carbon disappear? Because it didn't get white hot. It got red hot. So the only mechanism that I can imagine might be happening is that the carbon itself heated up the acrylic, turned it to liquid, and then the carbon floated on the top of the liquid acrylic, promoting even more heat transfer into the acrylic to allow it to liquefy and vaporize away through the carbon film that was on the surface of the boiling acrylic. And maybe that's what we saw previously when we saw black absorbed into our engravings. When we look at these craters of damage under the microscope, we need to see if there's any carbon particles that are visible that would confirm maybe this theory that the carbon was continuing to absorb the heat and transfer its heat to the melted acrylic. We seem to achieve more damage now than we did with the focus beam. We've got like a little crater that goes in, then it goes in sharply, and then we've got a flat bottom to the crater. Those little micro bubbles that are producing whiteness, remember? That's 100 times magnification. As I half expected, why have we got carbon that's maybe 2 millimeters deep into the acrylic? I think that tends to prove the point that that carbon was riding on the surface of the melted acrylic. When we run out of carbon, we run out of depth of cut. So if we burn the carbon away quickly, you focus and boil a very, very small spot, the focus disappears quickly and we don't get much depth into our engraving. So let's look at the small hole. And as we drop down into the hole, we can see a few bubbles, but not many. We can see a little bit of carbon that's been carried down on the liquid. Then we get towards the central core. It's fascinating, isn't it? Look how virtually every bubble has got a little bit of carbon associated with it. And look at that bit right in the middle. If I bring the table up a little bit more, note there's a bit of carbon on there. And that's the deepest point. So there is a very high intensity part of the beam, even though we're well out of focus. Although this is only data for a 3mm sheet, 450 nanometers is up there somewhere, which looks to be around about 92% or 8% absorption. 5 watts, 8%, 0.4 of a watt. So it really depends on what power heads I've got that will determine how much we can actually test this acrylic. It'd be nice to get a 70 watt laser, but I don't have such a thing. That simple experiment to see just how transparent acrylic is proved to be very interesting. First of all, same focus, same power, with a piece of acrylic in the way of the beam and without. Why the difference in power? I noticed something while we were doing the test that maybe you didn't. Now before we go out into the workshop and test it for real, I'm going to have to go through a little bit of atomic physics with you. Don't get worried, you know my attitude to science and It's very lightweight and irreverent. And I'm going to venture into this little zone here between physics and chemistry. Now this is a stereotypical picture of an atom, and it's a simulation. You could imagine this being our planetary system around the sun, where here we are, we've got the sun, and we've got all the planets orbiting around the sun. That's in essence what an atom is. But we've got these planets around here called electrons. Now, this is only just a very simple diagrammatic. We can go one stage on further and say, look, here's the core again with protons and neutrons. This is the solid part of the atom. But round the outside of the atom, there is a zone where all these electrons are flying round in random orbits. They're not a plane orbit like we've got in our solar system. These are orbits that are enclosed by a shell or a sphere. This again is very diagrammatic, and the scale is totally wrong. Let's just call that little bit the correct size. And this shell should probably be something like maybe 100 times the size that it is. There is so much space inside the shells relative to the solid part of the atom itself. To try and help people understand atoms, there are all sorts of different models. This is just another diagram. In this case, we've got all the electrons floating around in a flat plane, which you know not to be true from the other diagram. We don't need to know much more than the fact that that green thing there is a proton, and these black things around the outside electrons are about 1/2000th of the mass of something that weighs half of nothing anyway. So, you know, they're unimaginably nothing. And when these little things called photons, which if you remember have got no volume, no mass, all they've got is some sort of energy, and they travel at the speed of light. When one of these little magic bullets flies through the space that's inside an atom and accidentally, chance in a million like winning the lottery, and hits an electron, something like this happens. And all of a sudden from nowhere, we get a photon that collides with it. We get something called energy transfer. And that bit of energy is enough to push that electron out to a new orbit. That electron doesn't like to be away from home, and it won't settle in this extra orbit for more than about a few nanoseconds, at the most a microsecond, whereupon it will drop back to its home orbit, and in doing so has to give up the energy that the photon gave it. Now, although our colliding photon was at 450 nanometer wavelength, when this electron drops back down to its home orbit, the wavelength that this photon will deliver as it drops back down will be suitable for the particular atom that it is, not 450 nanometers. And even if it was 450 nanometers, it would not be coherent. It'll just be a random photon, not a tsunami of photons. There's a picture of our acrylic molecule. Each one of these has a little solar system on its own, with its own orbits and things. So we cannot say which of these was impacted by the photon. It could be any one of the electrons around any one of these elements. This is the mechanism by which this light is being created. Our stream of high energy laser photons has collided with some of the electrons in the acrylic molecules. We've created some light. Not laser light, but random light. The photons have given up their energy. They're no longer bits of laser light. They're no longer coherent. They're totally random. And that's the important thing from a safety point of view about when you look at this light. People are very fearful of laser light. This is not laser light that's emitted from this reaction. The laser beam is giving up its energy to create a different sort of light. The only time you need to have your laser goggles on is if you are working in a laboratory where you've got an open bench laser and you've got real laser beams which can bounce off of prisms, mirrors, lenses, and you are likely to receive true reflected laser beams. The laser beam is always pointing downwards, and the laser energy is being absorbed and converted into a different sort of light energy here. Now, this light energy could be just as dangerous in some ways because it's very, very intense. When you see me wearing sunglasses, I'm doing two things. I'm protecting my eyes against the glare of the sun, effectively, or against what you would normally see if you were looking at a welding arc. very, very intense light. Depending on the elements that are in that material, there may be some photons in the 200 nanometer region, which is the dangerous UVB and UVC region. So we're now going to go back into the workshop and we're going to look a little bit closer at this phenomenon. I thought that my relationship with acrylic and diode lasers was dead. I thought it was only useful for the CO2 laser, but now I can see a different possibility. Okay, so what I've got here is a lovely clear block of acrylic, piece of black paper behind it so we can see what's going on. I'm going to place that about 3 millimeters below the lens. There is no chance of smoke damage to the lens because we're not going to damage the material at all. The light is just going to enter it and pass through it. And I'm very confident that what we're going to see in here is something like a fluorescent tube effect, but the shape of the laser beam. So let's give it a try and see what we get. That was rather interesting, wasn't it? Now, the camera might not be able to show what's actually going on. Now, while I'm here, I'm going to do something else. Here I've got a piece of sort of semi-shiny stainless steel. And what I'm going to do, I'm going to pop that underneath there. When those blue photons come out of the laser head, there are 3 things that can happen. First of all, the laser beam can pass right the way through something that's supposed to be transparent and have no effect at all. Well, we can see that that's obviously not true here because there's some effect that's taking place because this is not fully transparent, this acrylic, as we found out. The second thing that can happen is it can reflect off of certain surfaces, and metal is one of the surfaces that it will reflect off. The third thing that can happen is that energy can be absorbed into the surface and converted into heat, and in which case the material gets damaged. So let's take both of those conditions and freeze frame them, and then we can comment on what we see. Well, much as I anticipated, in idiot mode, the camera is more of an idiot than me, because look, it just blows the picture out completely for those with and without the sheet. So I had to put the camera into manual mode and do some different pictures. So this is straight the way through with no reflection on the bottom. And as you can see, we've got a wonderful beam, quite a long focal distance here, and then it trails off. We can't really see the intensity profile in there, but it tells us what the shape of the beam is, and we can clearly see that at the top here it is about 3 millimeters diameter. Now this one, what we've done, we've put the stainless steel sheet under here, and if you look carefully you can see there is definitely a reflection that's coming back up, more over here than anything else. And up the top here, if you look, you'll see that we've got definitely a reflected laser beam. And just to prove the point what was going on, I've tipped the stainless steel sheet at an angle. The acrylic's gone over at an angle as well. But what you can see clearly here is we've still got our lovely laser beam, but now we've got our reflection, which we can clearly see. And this is the reflection as it exits at the top. Now what I must state is that going out is a laser beam. This is light caused by a fluorescent type effect, and this is much the same. This is just affecting the electrons and producing a small amount of fluorescence. But what's going out is definitely still the laser beam. So this is what you've got to be careful of. Reflected laser beams, because they can still be, just because they hit a surface, if it's a hard surface and they're not absorbed, then they're going to be reflected as a smaller but still a tsunami of blue laser photons. So this is the natural beam that we've got, and yeah, we can see that it is quite thin here, a focal point, but it stretches for quite a long way, and it's not that small as a beam. Now we can't see quite what the intensity profile there is at the focal point. We can see a sort of intensity profile beginning to happen here, because look, we can see the intensity dropping off as the colour drops off, and the amount of fluorescence, if you like, drops off. There's an interesting, strange phenomenon that I've noticed here. First of all, you can see what we've got here. We've got a patch of light, and you can see what we've got here. We've got a patch of light. Now light doesn't come for free, because the only reason that light is happening is because some of the photons in our laser beam are colliding and losing their energy as they hit electrons in this material. And that is happening all the way through here. This is recording effectively an intensity loss within the laser beam itself as it collides with electrons in this material. And then we get to this bottom face here, where again we've got laser beam hitting the bottom face here, and that laser beam is has not got enough intensity to damage the material, but it's certainly got enough intensity to excite the molecules on the bottom surface of this acrylic. Because two things seem to be happening. Number one, we get a little white light, which I said is not for free. That consumes laser energy. And secondly, look at this little bit just here. Can you see that? The light has disappeared. And it's not unique because look, it's also happened here and here. It almost looks as though we've got photons here which are anti-phase and cancelling out the photons that are coming in. I'm not a physicist, so I'm just looking at that and making an assumption on the basis of the facts that I know. So, lots to use and compare when we look at different laser beams in the future. 19, 20, 21, 22. The future is here. I've just realised I don't have to wait for the future. We've got a beam here which we can modify. I can hear you thinking to yourself, what sort of drug is this guy on? Let's go to the workshop and I'll begin to share my thoughts with you. Although the standard lens has got a very long focal range on it, it appears, I wouldn't say that it's focusing down to a very small focal point. It's indicative of the fact that it's working through the central part of the lens and there's not very much focus on it. All the focus is spread out over a long distance. There may be a point of maximum focus, but there's not much power at that maximum focus point. So what I'm going to try and do is collect the power into a smaller focal point by using a lens that I just happen to have, a clear glass lens. It's a 25mm focal length and it's a plano convex lens. I've got no idea where I got it from, but hey, it just happens to be in my possession at this point in time when I need it. And I've made myself a little adapter that fits on the end of the head and takes this 20mm lens. I'm pressing this lens in the correct way round, i.e. with the convex side upwards, and we'll see what sort of results we get. Now we've seen those results, we're going to put the lens in the other way round with the flat side up, what most people consider to be the wrong way. Let's see what effect it has on the intensity focus in the beam itself and also where the focal point is. We'll just pop that over the end of the existing lens holder and screw it into place with a little M3 grub screw. There we go. Ta-da! Well, there's the original beam. This piece of acrylic is 100mm tall. I'm fairly confident from what I've seen that most glass lenses are not the same standards as the zinc selenide lenses. 28mm seems to be a standard focal length for a glass lens. Now, whether this one is or not, I can't say, but what I can tell you is it looks as though the focal point here is round about 35. This is now a compound lens situation. What we've done, we've reduced the focal point here to something like about maybe 12 or 13mm, something in that sort of region, which is a significant change. And although it looks as though we've got a small focal point here, I would say that if we consider scale wise, this one looks a smaller focal point here. And this one, well, it's a bit difficult to say on this one because there's all sorts of things getting in the way. We've got this strange interference pattern at the top here, maybe. We're seeing less of it at the bottom. There is just a hint of it here as well. Look, there's a slight loss of intensity at the bottom in a sort of a strange band. You can see clearly now we've lost a lot of intensity below the focal point very quickly. Now, that in itself is pretty good news because it means that we are tending to focus more into one small area. Before I test this lens in the real world, this looks to be a better configuration because when we look at this, you'll see that it's a fairly small focal point, but it spreads over quite a long range. Well, that's not good news, because it means that the rays are coming together and focusing over a range. And over a range means that the power is being dissipated over this range. It's not focusing at one particular point. There is a focus point, but it's not using all the energy that's available. Whereas here, because we're focusing over a much smaller range here, I think we'll have a much greater focus. And if we take a look at this one, which is the upside down lens, it doesn't look like it here on the surface, but I suspect that this has got an even tighter focus than this one. When you look here, you'll see that this one has got a real glow to it. You know, there's a lot of rays that are running out here. These are the low intensity rays that are not really doing much. You may think that this one is probably looking a much better beam than these. I'm not going to prejudge it. What I will say is I've now got all the tools in place to test the performance of these beams. Test number one, I've got my little dot pattern. Number two, we're using black or coloured card. Speed will be the one thing that determines the power in the beam. If the intensity is strong, we will be able to run my dot test at maybe 600, 800, maybe even 1,000 millimeters a second and see a pattern. We need to do two things. First of all, we need to set the focus and find the best focus position, and that may well change with speed, much as it does on a CO2 laser. This is going to be quite a protracted, tedious set of tests to determine whether or not this pattern, this or this, is a better performing beam. I think I'm going to finish this session now, and I'm going to jump into doing a lot of tests. Thanks for your time. Fascinating stuff. It's not going in the direction that I thought it might go in. I'm still going to be stuck with this 5-watt laser. And I'll catch up with you in the next session.